Welcome all. So previous class we have discussing on heme proteins. That is, we have discussed that cytochromes A and cytochrome B. So previous class we are discussing on, let's say, that food chain, that is electron transports, that is from muscle tissue, that is, let's say, food. We can say that is from food to lungs, or we say that respiratory systems. This were the previous class, and we say that first is cytochrome B, then cytochrome C, then cytochrome A, and this A binds the oxygen. Okay, so this is the electron transport systems that we have discussed in the previous class, and we have discussed about of the cytochrome C we have discussed, and we have discussed cytochrome A. So cytochrome C, let me give quick recap. So cytochrome C, it is coordinately unsaturated, means it is these are the heme protein. Heme protein means that porphyrin ring is there. Porphyrin ring means, let's say this is N. So this, like this porphyrin ring is there, and here H is there. So this is coordinately binds with 4 nitrogens, and also here P and cis all are, this is binded. Okay, this cytochrome C. So this is coordinately unsaturated, but it indirectly interact by transporting electrons. Okay, that we have discussed in previous class. Also we have discussed about of cytochrome A. This is the last link in this electron transports, and it binds to the O2. And now we will discuss, so this much I think we have discussed in the previous class. Okay, so this cytochrome A, now we will discuss on that topic is cyanide poisoning. Cyanide poisoning. What do you mean by cyanide poisoning? So we know that this cytochrome A, it binds to cytochrome A binds to O2. Okay, now if this cytochromes A, but if CO and Cn minus also presents, then this cytochrome A will bind to CO or Cn minus instead of O2. Why? Because in spectrochemical series, in coordination chemistry, we see that O2 is comparatively a weaker ligands, or we can say it is neither too strong ligands, neither too weak ligands. This is comparatively weaker ligands, whereas Cn minus and CO, these are the pi acceptor ligands. Pi acceptor ligands are generally strong ligands. Okay, and if a strong ligands, and here that cytochrome A, it means that these are that one type of heme proteins. So in heme proteins we see that, but that porphyrin ring is there plus Fe atom is there, and this Fe atom is in +2 oxidation states, and this Fe2 plus ions, when it will comes to interactions with O2 and CO and Cn minus, if Fe2 plus H options to bind either O2 or CO or Cn minus, then obviously we can say from coordinations knowledge that Fe2 plus will bind to the strong ligands as compared to this is a weak ligands. So this Fe2 plus, because this is the 3D series elements and with the oxidation state of +2 charge, so that always very good binding with strong ligands. So this Fe2 plus will be binds with Cn minus and CO instead of O2. So if Fe2 plus will binds to Cn minus or CO instead of O2, then that is called that cyanide poisoning. Means it is binding to that cyanides or carbonyl groups instead of binding to the oxygens. So this phenomena is called the cyanide poison. Okay, so they say that if cytochrome A binds to Cn minus or CO instead of binding O2, then it is called cyanide. It is called cyanide poisoning. Okay, so this phenomena is called that cyanide poisoning. Okay, why it will bind? Because this Fe2 plus having a plus 2 oxidation state, this is how always it will binds more strongly to the stronger ligands. So that is pi acceptor ligands. The stronger ligands, we see that like halogen groups, then oxygen donors, then nitrogen donors, then pi that is that groups, that is what that groups chelating ligands like En. After that will comes the pi acceptor ligands. So spectrochemical series will be like this side. So here in these sides will be these are the weaker ligands, these are the weaker ligands, and these are the strong ligands. Okay, towards the left are stronger ligands. So always this Fe2 plus will binds very much stronger to the stronger ligands. Okay, this is the spectrochemical series. So that's why it will binds to the Cn and CO minus if it has the options of binding O2, CO and Cn minus. This always prepared to bind CO and Cn minus. Okay, so this phenomena is called that cyanide poisoning. Now if cyanide B means we have discussed in the previous class. This is the hemoglobins and myoglobins that we have discussed in the previous class. This cyanide B we have discussed in the previous class. This is if R1 equal to R2, that is equal to CH2 and CH2, it is found in cytochrome B or hemoglobins and myoglobins. Okay, so this is the structure of this, and if this R1 and R2 equal to CH2 and CH2, then that is called cytochrome B, and that is found in hemoglobins and myoglobins. Now this hemoglobins and myoglobins, if cytochrome B or hemoglobins or myoglobins, if it binds, okay, this hemoglobins and myoglobins, it can't bind Cn minus or CO. Okay, but methemoglobins bind Cn minus or CO. Okay, so we need that cytochrome, hemoglobin and myoglobin should bind the Cn and CO minus to release the oxygen or to remove from the systems. So what we will do that we need that, since this hemoglobins and myoglobins not able to bind Cn and CO minus, but methemoglobins can bind to Cn and CO minus. But the problem is that methemoglobin is exist very less. So methemoglobin is very less compared to hemoglobins and myoglobins. So for that we have to convert into methemoglobins. This hemoglobins and myoglobins, we have to convert them to the methemoglobins so that it will bind to Cn and CO minus, and after it binds to Cn and CO minus, it will release from the systems. So that we need. So for that, what we will do that we will convert these hemoglobins and myoglobins to the methemoglobins. How will convert that? To convert hemoglobins or myoglobins to methemoglobins, what we will do? We will do some treatments. So what are the treatments? Like amyl nitrate injections or sodium nitrate injections. So by amyl nitrate injections or sodium nitrate injections, we will convert that HB or MB, that is hemoglobins and myoglobins, to methemoglobins. Okay, and these methemoglobins will bind strongly to the Cn minus, and these methemoglobins bind strongly to CO and Cn minus, and it helps to remove it from the systems. Okay, so now we will discuss the another concept, which another cytochromes, which cytochrome P450. So why this name is cytochrome P450? Because what you see that in UV visible spectroscopy, we see that the solid bond, so solid band of this cytochrome P45 is found. It is observed at 450 nanometer. 450 nanometer in solid band. Okay, that's why its name as cytochromes P450. So it is a type of cytochromes which observes at 450 nanometer, then the 400 nanometer in solid band. That's why you called it as cytochromes P4550. So it is a type of cytochrome in protein. Okay, and what you see that this cytochrome P450, it is found in kidney. And what is the functions of the cytochromes? It facilitated the cleavage of O2 bond. Okay, so what the work is, it will cleavage the O2 bond. So it will present in the kidney, and whenever we eat something, so that hydrocarbons which is insoluble in waters, what will do it, what the work of this cytochrome P450 is, it converts that insoluble hydrocarbons to the to the water soluble compounds, like it may be alcohol, it may be acid, it may be epoxides. So it converts, or it oxidized the water insoluble hydrocarbon to water soluble compounds like alcohol, acid, epoxides, etc. Okay, so its work is to convert that water insoluble hydrocarbon compounds to water soluble compounds like alcohols and acid. So it oxidizes it. Okay, so that will be excrete from the urine, because that compounds, which compounds will become water soluble, that will be easily excrete from the urine because it is water soluble. So the work of that these proteins, that this heme protein cytochrome P450, it is available in the kidney, and its work is to facilitate the cleavage of O2. How it will do? It will oxidize the water insoluble hydrocarbons to the water soluble compounds. Like if I say the examples, let's say any hydrocarbon is there, and if you have this cytochromes P450, then what will do? It will converts into alcohol. Okay, this is water insoluble, water insoluble, and this is water soluble. Like this, if you have any compounds like aldehyde groups, then if you give the cytochromes P450, then what it will do, it will convert into acids. That will be convert into acids. Similarly, if you have any this type of groups, like if it says this type of groups, if you have that cytochromes P450, let's say this type of groups CH, then it will convert into epoxides. Okay, 1 2 3 2 3 epoxide will be formed. So this is the work of the cytochrome P450. Okay, and how the structure of this cytochrome P450, structure of cytochromes P450, how the structure it will look. So you know that this is the heme protein. Heme protein means that porphyrin ring is there. Heme protein means porphyrin ring plus Fe is there. So how the structure will be? Porphyrin ring we know. So I'm not drawing the whole structure of this porphyrin rings, like it has that, sorry, this type of 1 2 3 4 5, like that all the groups are there, they have the chains like that. Okay, I'm not drawing that the sorry, it has that type of this type of groups, and they have that double bonds are there that we have drawn already. So I'm not drawing. So like this is there. Okay, and one Fe will be here, and these are the bonded with this. Okay, and it has that one bond each. This is porphyrin plus Fe. So one is here. Histidine will be there. Okay, histidine groups. Okay, this type of histidines will be there, and so this is the one that porphyrin rings. The Fe is first coordinate with 4 bonds with nitrogens of this porphyrin rings, and one will be with the histidines, and other will be that in absence of oxygens it will be bind with H2O. Let's say OH2. Okay, with binds with water, and whenever this oxygen will binds, if you do the oxygens, then it will bind that Fe, this N groups, this porphyrin rings. I'm not drawing that, so here that N will be there, here O2 will be binds. Okay, so that is the structure. Oh sorry, they are not histidine, sorry. Here you will be have the cysteine groups. Okay, not histidine, there will be cysteine. The protein will be cysteine protein will be there, and before binding with oxygen OH2 will be there. After O2 it will bind to O2. Okay, so this is the structure of P450 cytochromes P450. Okay, so what you see that here it is in +3 oxidation states and it is in +2 oxidation state. So here that Fe and this OH, Fe2 plus O2, in case of plus 2 oxidation state, bond order is 2, and wherever this, I can write here. So here this is P plus 3 oxidation state, in plus 2 oxidation state this Ap2 plus O2, here the bond order is 2, whereas for Ap3 plus O2 or O2 minus, here bond order is 1.5. So, and this is that reduced form, and this is the oxidized form. So here that bond order is decreasing from, so bond order is increasing from here to here, bond order is increases. So what you say, the stretching frequency of, so what you say, that stretching frequency of decreases in Ap2 plus, or that is says Ap and O in oxidized form or in Ap2 plus oxidation states. Okay. So these are all about of, we see that cytochromes A we have discussed details, and heme we discussed that non-heme groups and heme groups we have discussed. So now we move to the next topic, that is transport of oxygens and storage of oxygens. Okay. So in this previous class, what I have discussed, that we discussed that electron transport from muscle tissues to lungs, and the transport system is first cytochrome B, then will come cytochrome C, then will come cytochrome A, and it will binds to O2. Okay. So this is the electron flow that we have discussed in the previous class. So today class we will discuss on the topic of oxygen transport and storage. So today's topic will be the oxygen transport and storage. So in this we will discuss the two things, the same, that is heme proteins and non-heme proteins. Heme proteins and other is non-heme proteins. So in heme proteins we will discuss, heme protein means porphyrin ring plus Fe, that is irons. That's why we have discussed in the past class about details about of that porphyrin ring, because this porphyrin ring, whenever heme proteins will comes, then it always say that porphyrin ring will be present. Okay. Whenever non-heme proteins means no porphyrin ring plus any metal atoms, maybe it is Fe or maybe sometimes copper is also present. Okay. This is for non-heme proteins. Okay. So this porphyrin ring is very important. That's why I have discussed in the past class detail about of this. Whenever we discuss about a heme protein means porphyrin ring present or not, that we will discuss. So heme protein means porphyrin ring is present, non-heme protein means porphyrin ring is not present. Okay. So now we proceed with about of this heme proteins. Okay. So first we will discuss about of the heme proteins. Heme protein. Okay, here we will discuss that two example we will discuss. One is hemoglobins, that is Hb, and another is myoglobins, that is Mb. Okay. Now this, in this transport of oxygen will happen in which way? That is from lungs to muscle tissue. Okay. This is the oxygen transport will happen from lungs to the muscle tissue. In previous class we have discussed the electron transport, that is from muscle tissues to lungs, that we have discussed in previous class. Okay, so today we will discuss the oxygen transport from lungs to the muscle tissues. So in this whole oxygen transport, we will discuss that oxygen transport is happening from lungs to the muscle tissues. Okay, so first we will discuss about of the hemoglobins, then we will go for the myoglobins. And note that this hemoglobins, it is made up of 4 subunits, and each subunits, so it is like says one subunits plus one subunits plus one subunit. So all subunits are same, and this one subunits is equal to myoglobin. So myoglobin is the part of this hemoglobin. So if you know about a hemoglobin, then we easily understand about of the myoglobins. So this hemoglobin is 4 subunits, and one of the unit is called that myoglobins. So one unit is myoglobins. Okay, so we'll discuss in detail about our hemoglobins and myoglobins. We'll just give a quick quick introductions on it. Okay, so we'll start with myoglobins. This is myoglobins. Okay, so past topic is hemoglobin, that is HB. So if you talk about a hemoglobin, it is a heme proteins, a type of heme proteins. Okay, so heme protein means we understand that porphyrin ring is there plus iron is there. Okay, and next it is the fast protein that is crystallized. Okay, and next it is found in red blood cells, that is called RBCS. Okay, and this red blood cells is red in color due to the presence of this hemoglobins. Okay, so if hemoglobin absent in red blood cells, then this red blood cells may be colorless or some other colors, because this red blood cells is red in color due to the presence of this hemoglobins, some other colors. Okay, and what you see that this hemoglobins, the general structure, this is the general structure, how it looks, that you see that porphyrin ring is there plus Fe atom is there, because this is the heme proteins. So its structure will be porphyrin ring is there. Porphyrin ring means that N, here N, that we have discussed from past class itself, how this will be. Let's say okay, this type of structures, and it has the bonds here, bonds here. Okay, this type of structures, and it has that double bonds here. Then I will leave here, then here, then I will do here, then okay, this is the structure of porphyrin ring, and here Fe atom is there, and Here after that what will there, one side is n histidine will be there. Okay, n histidine proteins, 1 2 3 4 5 5. Okay, this proteins, and here we see here this. Okay, this type of proteins here, and here that, or sorry, this is the three, four, five. Okay, so this type of proteins, and here let's say, or I can draw here 1 2 3 4 5 6. This type of groups is there with the pipe rings, and here if we say that hydrogen is there, and here there's double bonds, and let's say this, then double bonds, here one pair, then this type of structure histidine is there, and here let's say protein is there. This is the structure of this, or I can draw it very easy. Let's say that groups is n, and okay, this type of groups. Okay, so here I can join. Okay, so here this, and I will do here. Okay, this is the propane ring. So here, so iron is there, and here that histidine group will be there. Sorry. Okay, here that one side histidine is there, so 1 2 3 4. This type of group, 2 3 4 5. Okay, here protein is there, and here hydrogen is there, and let's say here one pair. This is the structure of general structure of hemoglobins, and here you see that any backend side is there. Okay, here that backend side. Okay, so this is the general structures of hemoglobins, and here that what groups are there that we have discussed in the previous class, that here that R1 is CH2 double bond CH2, and here that groups are, what type of groups are there, here also CH2 double bond CH2, and that we have discussed in the previous class. If I talk about exact picture of this hemoglobin, so here that what we says that this for hemoglobin and myoglobin, this R1 and Rp equal to CH2 and CH2. Okay, so this is the actual structure. Here R1 and R2 has to be CH2 and CH2, and here it has that N histidine will be there, and here the backend side will be there. This is the exact structure. It is the actually structure of the hemoglobins. Okay, so I'm not doing that parts. Okay, so this R1 and R2, that is R1 has to be CH2 and CH2. That type of structure is that general structure of that hemoglobins. Okay, so we generally look that here that porphyrin ring is there, and that is coordinated to all this uh, with the nitrogens of these porphyrin rings, and this spore is coordinated by the porphyrin rings, nitrogen atoms of porphyrin rings, and another is uh, bond with the histidines. Sorry, imidazoles. This is not histidine. This is the imidazole of histidines. Okay, and another is the vacant sites. I think that is the vacant sites. Okay, the cis coordinates is vacant sites, or maybe water is present. Okay, so this is the general structures of the hemoglobins. Okay, now what you see, this hemoglobins can be two way it will exist. Either it will this so this hemoglobins, the work is transport of O2 from lungs to muscle tissues. Okay, this is the functions of this hemoglobin. So whenever it is has water, then we call that is oxyhemoglobins, and when oxygen is not present, then it's called the deoxyhemoglobin. So here we will not discuss about of the oxidized form or reduced form. Here we are talking about of this transport of O2. So here whenever this hemoglobins it has that oxygen, then we call it as that oxyhemoglobins, and whenever this oxygen is where oxygen is present, and whenever this oxygen is absent, then we call as deoxyhemoglobins. That is absence of O2. Okay, so we'll discuss this hemoglobins or myoglobins or other proteins like non-heme protein also we'll discuss in the presence of oxygen or in absence of oxygen. In presence of oxygen we call as oxyhemoglobins or oxy whatever the proteins, and in absence of oxygen we call as deoxy and that proteins. Okay, so this first we will discuss. So hemoglobins is exist in two forms: oxyhemoglobins where oxygen is present, and deoxyhemoglobins when oxygen is absent. Okay, so now we will discuss oxyhemoglobins. First we say that deoxyhemoglobins, another is oxyhemoglobins. So it is very important to do the structure. So in deoxyhemoglobins, what you see here is that, so this Fe, this Fe, it is exist in +2 oxidation state. Here Fe is in +2 oxidation states for case of hemoglobins. Okay, for hemoglobins, this Fe is exist in +2 oxidation states. So Fe is in +2 oxidation state. Here also Fe is in +2 oxidation state, but here that Fe is in +2 oxidation state and it is in high spin, and here Fe2 plus is in low spin. So whenever you do this Fe +2 oxidation state, that is equal to D6. Okay, D6 high spin. When you do that electronic, so you do that 1 2 3 or 5. Okay, whenever I fill the electrons D6, so 1 2 3 4 5 and 6. So this is high spin. So octahedral case, we feel like octahedral, not tetrahedral. So this is in a octahedral structure, so we feel octahedral. So this electrons will be, this is the high spins, so no pairing will occur. First 3, sorry, this is 3 4 5 and 6. So we see here that this is the T2G and this is the EG. It means that this is dx square minus dy square and that is dz square. This is the dxy, dyz, and dzx, like that. Okay, so and whenever you peel for this is the low spins 1 2 1 2 3 4 5. So this is the d6 low spin. So electron will be 1 2 3 4 5 and 6. So whenever you peel the electrons, here again 3. Okay, so electrons are 1 2 3, and since this is a low spin, so pairing will occur 4 5 and 6. So here we see that here this is the T2G, this is the EG. So no electrons in this square minus d square and dz square. So what we see here, that due to the electrons are present, due to electrons is present in dx square, dy square or dz square, this have some repulsions will started. Okay, so here what happened, that due to electron presence in EG, that is dx square minus dy square or dz square, the repulsions happen between electron in dx square minus dy square or dz square and lone pair electron of n, this n from pr ring. Okay, so this is n from pr ring. So this here, this lone pair electrons, here lone pair is there, sorry, not here. So here a lone pair is there. So this lone pair and this electrons of dx square have the repulsions. So due to this repulsions, this Fe atom will be not stay here. This Fe atom will move somewhere here out of this porphyrin rings, not in the plane. It will stay outside of this ring, not stay in the cavity. Okay, so due to that due to the repulsions between electrons in dx square, dy square, dz square, and lone pair of electrons in nitrogen atoms, that is pair rings, that Fe atoms will move outside the PR ring, porphyrin ring. So in the cavity of the porphyrin rings, that Fe atoms will not stay, it will go outside the porphyrin ring. So this structure will becomes like this. Here nitrogens, here nitrogens. So here that, let's say that porphyrin ring that is there, and they have this type of things that we have not, I'm not drawing. So this is that the structure. Then due to this lone pairs, what happened, that these Fe atoms will move somewhere here. Okay, so from this distance, so distance between this porphyrin ring is about of this 40 picometer. Okay, so distance of 40 picometer from this porphyrin ring, it will move. Okay, so now how will be bonding will occur? So here it will there. So like this. Okay, so this Fe will be not stay in the cavity of the porphyrin ring. It will stay outside the porphyrin ring. Okay, so this the distance of 40 picometer. Okay, it will stay at the distance of 40 picometer. So this is the structures of for deoxy hemoglobin, and one side is the vacant sites. Okay, so it is coordinated by 1 2 3 4, and one will be the histidine will be there, sorry, imidazole of histidines. So that, okay, that histidine will be there. Right, okay. this histidines 1 2 3 4 5 here N will be there, and here any partner will be there. Okay, so this and this. Okay, this histidine will be there. So this is the structures of deoxyhemoglobins. And for case of oxyhemoglobins, what we see that plus 2 oxidation states here, that no electrons is in the EG state, EG or DI, that is dx square, dy square, dz square. There is no electrons are there. Here there is no, so no such kinds of things. These things will not happen. So here no repulsions occur between the lone pair of nitrogens or porphyrin rings and with that Fe atom. So no repulsion will occur. So here that Fe will stay inside the cavity of the porphyrin ring. So here let's say here NN. These are the porphyrin rings, the structures here and here. Then this Fe will be present here. Okay, so here like that, same that will there, and what happened there? Here that imidazoles will be there. Okay, imidazoles, and here for protein groups. Sorry. So this type of structure will be, we will see. Okay, this is the case of that oxy groups. And what we said that here after that oxygen will comes, oxygen will binds. So this will bind like this, and this angle is somehow 130-degree angles we will find here. Okay, so oxygen will bind. So here from oxyform to we are adding the oxygen, so oxygen will bind. So here in this case no oxygen is there. So in this case some water may be there. So whenever you do the oxygen binding, then oxygen will come here. Okay, and now what happened that this structure I'm drawing again this oxy hemoglobins. Okay, try to draw that, or you can draw here. So here will be the hydrogen bonding will be there. Okay, with this and this hydrogen bonding will be there, hydrogen bonding. Okay, so or if I draw here, so oxyhemoglobins, if I draw, so let's say this N, so if Fe is here, so this is like this, and if here let's say that histidine is there, one, two, three, four. Okay, so okay, so this type of histidine. So here that hydrogen atoms is there, here is protein also there. Okay, so now here that oxygen will comes this, and this angle is 130-degree, and here will be the hydrogen bonding will be there with this and this oxygen, this hydrogen bonding will be there. Okay, and one more thing we have to note it is that since here Fe atom is inside the cavity of the porphyrin ring, okay, for oxyhemoglobins, and for that deoxyhemoglobins, this this iron is outside of the porphyrin ring. So the bond length between this nitrogen of this porphyrin ring and this iron is about, we can say this is longer than in this case, because here that the distance is less and here the distance will be high. So you can say that this is how we are discussing here, that here the deoxy form, deoxy hemoglobins, here is that oxyhemoglobins. So here the distance between nitrogens and Fe which higher than distance between nitrogen and iron in case of oxyhemoglobins. Okay, so here this is the, because this iron is outside the porphyrin ring. Okay, here it has less distance between nitrogen and iron. Okay, because this iron is inside the cavity of porphyrin ring. Okay, so these are the some points that we have to discuss, difference between this deoxyhemoglobins and the oxyhemoglobins. Okay, so now we will move to that next part, that is that compositions of hemoglobins. Okay, so here both are exist in the post oxidation states, and its structures for deoxyhemoglobins, that Fe is exist in outside of the porphyrin ring because of the interaction, because of that repulsions between that lone pair of nitrogen atoms of porphyrin rings and the Fe atoms, that is electrons in dx square and dy square or dz square. Okay, whereas for oxyhemoglobins that case is not happened here because no electrons in dx square and dy square or dz square. Okay, now we will move to the next topic, that is composition of hemoglobins, that is Hp. Okay, so here what we see that this hemoglobin is made up by 4 subunits, and these 4 subunits has 2 subunits, and it has again 2 subunits. Why I am doing subtract dividing this 2 subunits, because these 2 subunits have the alpha units, and these are the beta units. Okay, and these alpha units have 141 amino acids, so each subunits has 141 subunits, 141 amino acids, and this beta units has 146 amino acids. Okay, so it has 146 amino acids and it has 141 amino acids. Now what we see is that these compositions of amino acids, let's say this is amino acid, sorry, this is hemoglobins. It has 4 subunits. So let's say this is one hemoglobin, this is one hemoglobin, one subunit, this is one subunit, this is one subunit. So each subunits, they are in they are having some interactions in between, so that they are in a group. Okay, they have one interactions, so that they are in a one group. So these interactions It's called that salt bridge. So what is these interactions? So if you see that amino acids cases, the amino acids, how it look like, that CH2, that says R1 and CH, and one side we have that NH2, and one side we have that OH. This is the amino acids, or I can draw RS and CH. Let's say here NH2, here OH, and another amino acids NH, and here CH, CH2, and here you have that R double dash. Okay, so whenever you do that here, that bonding you will do, then you will do here, sorry, so what you do that here, if you do the peptide bonds, then minus H2 will remove, water will be removed, then what you will get here, that R1, R dash, and C, NH2, H, here will be CO, and here will be NH, and COH, this R2. So this is the aminos, this is the protein of a small chain, that is peptide bonds. So this bond is called the peptide bonds. Okay, this bond, this is called the peptide bond. Why I am interested with this peptide bond? Because you see that these interactions, they have this interactions, they have this. This is the like, this is one subunits, one subunit. This is one subunit. This is one subunit. So they have this. They have this, all the subunits. These four subunits, they have they are grouped because of this interaction. This interaction is called salt bridge interactions, and this interaction is the electrostatic interactions. And these interactions happened because of this. Let's say this amino acids, RTS, CH, and COH, and NH2, and another is, let's say, C, here NH2, and here H, here COH, and here. Okay, so here this. Okay, so here this R double dash. So this and this have the interactions. So this interactions actually binds this, bind this salt bridge. So this is the salt bridge, and this is the interactions of, this is the electrostatic interactions, electrostatic interactions between this NH2 and CO2 group of amino acids. Okay, so this salt bridge, that makes this amino, four subunits of hemoglobins in a one group. Okay, now what it says that we have this oxy and deoxy forms. Okay, this hemoglobin is exist in oxy and deoxy forms. So whenever you discuss about of this deoxy hemoglobins, in this case it has a lot of strain is there. Why strains? Because let's say this F is outside of the rings and it is bonding with these four nitrogen atoms of this permanent rings, and here will be the more strains, more tens will be there, and whenever you add to the oxygen, then this Fe will comes to this inside of the porphyrin ring. So as iron comes to inside of the porphyrin rings, the strains will be removed. The strain will be removed because here that Fe is inside the porphyrin ring. So this deoxy form is also called the T states. It is also called the T states, that is tense state, or we call as this is the T states. And whenever this iron will come inside the porphyrin ring, that strain will be removed, and whenever this strain will be removed, then that this type of salt bridge will be break. Okay, so here this deoxy forms a lot of that this salt bridge will be there. Okay, this salt bridge between these amino acids, and there will be a lot of salt bridge. Salt bridge means there's electrostatic interactions between this amino acid and CH groups. A lot of this type of salt bridge will be there in deoxyhemoglobins. But whenever this Fe, whenever this movement of this ions comes from movement of ions and this imidazole of hydrogens, it comes to the inside of these rings, then a lot of that this salt bridge strains will be break. If this salt bridge will break, then the strain will be removed. So whenever this strain, this electrostatic interactions, these salt bridges are there will be highly tense states. That is in the deoxy forms. But whenever these irons and these imidazoles will move to this inside, then the lot of this salt bridge will be breakdowns. It means that lot of this stress will be removed. So this oxyform is called relaxed state. Relaxed state, or you call that R state. Why? Because here a lot of strain is present. This I will remove here. Lot of strain is present due to lot of salt bridge. Due to lot of salt bridge present. And this salt bridge means what? Salt bridge means that interactions between COH and NH2. Okay, and here that this it will relax state, because here breaking of salt bridge happened due to movement of Fe and imidazole. Okay, so we are discussing about of this compositions. We are discussing on composition. So we see that this there will be that interactions, and this interactions that made this 4 subunits in a one groups, and this interactions is this that we have discussed. And now one more things we have discussed, that is that in a peptide, in a hemoglobin, what it has the two parts. One is polar part, another is non-polar part. Non-polar part. So in polar parts, what is says that hemoglobin has two parts. One is polar part, non-polar part. Polar part means there will be electronegative difference will be there. Electronegativity difference. And non-polar part means no electronegativity difference. Okay, so let's say this is that uh, hemoglobins. Then these two parts is there. One is polar parts and one of which non-polar part. Okay. So what we see here that this polar part and non-polar part, how the composition will be that all non-polar part, let's say polar part I am saying P, and non-polar parts I am saying H and P, then here that all non-polar part will be inside and polar part will be outside. Okay, so similarly here also this is polar part, here is non-polar part. Similarly here non-polar part, here polar parts. Similarly here non-polar part, this is polar parts. So like this the compositions will be said. Okay, so inside all are polar non-polar part and outside all are the polar parts. Okay, so here what is this hemoglobins, the structure or something like this, and its structure is, we say that the general structure is somehow like this, means inside that iron is there, and also you see that hemoglobin inside each non-polar part is there, outside each polar part is there. Okay, so what you see that here inside iron is there, and inside also non-polar part is there, and outside polar is there. So whenever this water will comes, and this Ap is in +2 oxidation state, because hemoglobin that iron is there in +2 oxidation state. When this water will comes to interact, and water is a polar parts, so and this polar and polar will get repulsed. So here this polar part is there, so they will get repulsed, so water will not able to enter inside the hemoglobins. So if water will inside into the hemoglobin, let's say this is Ap in +2 oxidation state, if water will enter, then what will happen, this Ap will convert into +3 oxidation states. Okay, and if it is +3 oxidation state, then Ap3 plus will not able to interact with O2. This interaction will not happen. That's why this it has to be in Ap2 plus. So to protect this iron in Ap2 plus, it will be composition will be something like this, that the polar parts are outside, so that it will be repel the any polar group comes to this hemoglobins, so that this water will not able to enter and not will change this Ap2 plus to Ap3 plus. Okay, so what is say that this Ap2 plus interact with Ap2 plus, and here this hemoglobin, this is the bio and transport O2. But whenever this Ap2 plus interact with water, then it will convert into Ap3 plus, and this Ap3 plus will not bind water and not able to transport O2. So that hemoglobin composition is like that, so that it will not enter the water, and it will not change Ap2 to Ap3 plus, and it will able to transport the oxygen. Okay, so this that whenever this Ap2 plus convert into Ap3 plus with water, then it will become Ap3 plus, and it will not able to transport O2. On that case we are called that is hematins or hemins. The hematins, this hematins, this hematins or hemins, this is the phenomena, 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 this is the phenomena when Fe2 plus interact with water and it converts into Fe3 plus, and this Fe3 plus O2 not interact. So this process is called that hematine or hemine. Okay. And next two effects are very important. One is cooperative effect. Cooperative effect. So what do you mean by this cooperative effect? Okay, one is we understand study that cooperative effect. Cooperative effect means we have that hemoglobins when that cooperative effect okay. So this is the phenomena. The phenomenon of additions of one the phenomena of additions of dioxygen additions of dioxygens to one subunits of hemoglobins hemoglobins will encourage the other dioxygen to add other subunit of hemoglobin. Is called the cooperative effect. It means that you have that hemoglobins, let's say hemoglobins is there, and if you add O2 then it will become HbO2. Okay, let's say at the rate is K1, and after that HbO2 is there, when and again if you add O2 then it will become HbO2 plus 1, and this is become 2. O2 and another HbO2, to add another O2, then let's say this is K2, then another add you add, then this will become HbO2 3 and HbO2 3. Another if you add O2 then it will become K4, then it will become HbO2 4. So what he says here is that here that first times whenever it adding, here in this case that K1 will be very slow. Okay, the rate of K1 will be very slow. The rate will be very slow. After that it will encourage. So first will be difficult. After that it will very become easy. So rate of, if you compare the rate, then K4 will be very high, then K3, then K2, then K1. Means past case it will be very difficult. After that it will become very easy. Okay, that's say that the phenomena of additions of dioxygens to one subunit hemoglobins will encourage the additions of other dioxygens to the other through the subunits of the hemoglobin. So first time it will be difficult, After adding one time, it will become very easy and it will goes to very easy. Okay, so that effect is called the cooperative effect. And next, another topic, another effect is that is Bohr's effect. Bohr's effect. Okay, so in this Bohr effect, what it says that it is pH dependent. It is pH dependent. Okay, so what it says that if pH will be increases, then the affinity to O2 also decreases. Okay, so if pH will decreases, then so what you see here that this is the transport of O2 from lungs to muscle tissue. So what we say in the muscle tissues, we have that, like if we have that glucose like C6H12O6, and if we are adding that O2, then what happens that they will convert into carbon dioxide plus water plus we get some energy. So this carbon dioxide and water, what they will react, plus water, they will react and uh, they will form that carbonic acid, that is H2CO3 plus they will form this type of carbonic acids. Okay, this is carbonic acid, and this carbonic acid is what, 2H plus CO3 2 minus. So what is that concentration of H plus is increasing. Okay, in the muscle tissues, concentration of H plus is high, so we know that okay, so in the lungs, what you see that concentration of H plus is high, so you see that concentration of H plus is high, then pH will be decreases. Okay, because pH is negative logarithm of H plus concentration. So if concentration of H plus is high, then pH is decreases. So in the muscle tissues, concentration of H plus is high, it means that pH is decreases. So if pH is decreases, then affinity to oxygen is decreases. Okay, so affinity to oxygen will be decreases. So what is that if affinity to oxygen is decreases, means that hemoglobins is that oxygen transport. Okay. And hemoglobin is transport, this transport. Okay, so hemoglobins, this transport oxygen, but in muscle tissues, in muscle tissue pH is less because H plus concentration is high, so affinity of O2 will be decreases. it means that it will release the O2 in the muscle tissues. Okay, so if the graph, if you look, then here that saturations of O2 with this is the percentage of saturations, with O2, and this is the partial pressure. This is high. So, and we know that this MB is independent of pH, whereas this HB, that is hemoglobin, is dependent on pH. Okay, dependent on pH. So this car we will get, that is for this is for this hyperbolic car is for hemoglobins, and that this is for that sigmoidal car is for hemoglobins. Okay, and that last we will discuss, that is myoglobins. Today class, the last topic is myoglobins. So it is the one subunit of hemoglobin. Okay, so this hemoglobin, that is transport the oxygens, but that needed to store that oxygens in the muscle tissue, so that work will be done by myoglobin. So myoglobin, it store O2 in muscle tissue, and it binds O2 more strongly than hemoglobins, and it is pH independent, and that other things, that structure and composition are same with hemoglobin, because it is the one unit of the myoglobins. Okay, so today up to this, thank you.